I'm going to directly share the thing, the whiteboard. Is it visible to you?
Yes, sir, it is.
So I have finished already these topics in your other classes. Let's see some. Yeah, this is the single phase rectifier, I should say. And before introducing the single phase rectifier, we have already learned some of the basic concept of the rectifiers, like for the half wave rectifier with purely resistive load, inductive load, and for a this is voltage, right, as a load. Today I'm going to introduce article 5.3 from Nirvana. Still I am continuing from Nirvana. Single phase these rectifiers. Normally the rectifier we have that I have already shown the basic diagram of the rectifier to you. That is the last moment, if you remember this. Actually, this is the model of the source voltage. That means that has come from the utility. Utility means what does it mean by the utility?
So the power distributor, sir, Tesco, PDB.
DPDC.
That means who will provide the power, right?
Yes, sir.
So this one, what I have already drawn, look at here. So this is the source voltage and with source inductance. There is a model of their voltage source. Now we shall draw the rectifier circuit like this. Try to remember how I draw. First you draw one leg and then another leg. This one is called one leg, this one is called another leg. So you draw it and you name the diodes. This will be D1 and this will be D2 and this will be D3 and this crosswise. Okay?
Yes, sir.
That will give you the idea of how the current will flow through the diode. And then from this utility supply, you connect the supply two legs like this. And from there, from here, you just put a load. This is the load, huh? So load. From here to here, we will get the output voltage, and this is your output current. So now, if we analyze this one, let us start with LS equal to 0. Then eventually we'll discuss when LS is equal to not 0. That means LS has a finite value. Okay. So now I'm taking this thing off. So again, we will rectify. single phase, of course, it is okay. So you just draw the source voltage like this and draw the phase rectifier as what I have already drawn. So this is your D1, this is your D2, this is your D3, and this is your D4. You can turn off your mic because sound is coming noise. This will be VS. VS will be good to VS sign off. Omega T. This VS is RMS value or peak value? I'm asking question.
Sir,
Sir,
This
peak
VS,
value.
no, this
peak
is
value,
RMS.
sir.
This is RMS value. VM will be root 2 VS. Okay.
Oh, yes, sir. I'm meaning, sir, the small VS, sir. Isn't it the peak value, sir?
Small VS is the instantaneous value. Instantaneous value, you understand?
Yes, sir.
Suppose you are plotting this one. So this is your pi and this is your twice pi. This value will be VM, and that is nothing but root 2 VS. Where VS is the RMS value, right? Suppose what is the single phase RMS value in our country, in Bangladesh? Can anyone tell me this?
220 to 240 voltage.
Okay. VS in Bangladesh, it will be 22, actually 234. And what is your omega equal twice pi FF? F. What is the F here?
Sir,
Sir,
50 hertz.
50.
50 hertz. Okay, so this voltage has applied to your rectifier, and let us put the load as first resistance. Although we have discussed that thing before your midterm, but I am still reviewing it for the purpose of better understanding. So that will be your say ID, and this will be your say VD. VD is the voltage across your resistance. So VD will be your, we can write of ID. So what will happen? Suppose this is the positive half cycle that we got here. Look here, this diode is forward biased. So current should, if it is the source current should start going this way, this way, this way. Are you following my pen?
Yes, sir.
Yes, sir.
This way, this way, this way, this way, this way. So this will be your path of the current, right? So now current is flowing from this point to this point, that will be here, and we got the output voltage VD. And during this positive half cycle, and your D3 and D4 will not be conducting, it will be reverse bias. Am I correct or not?
Yes, sir.
Okay. This time, this one here. So if you apply the Kirchhoff voltage, then you can say see that VD equal to Vs for omega t equal to pi, that means for positive half cycle. So current will flow, and what will be the wave shape of the current? What will be the wave shape of the current? ID will be Vs by R. So what will be the wave shape of Vs? Can you follow it? Wave shape of Vs is equal to sinusoidal, right?
Yes, sir.
Of course, the ID will be also sinusoidal. And since there will be no phase lag,
It will be in phase.
yes. So, and the magnitude could be different, of course. Because this will be the current scale, another will be the voltage scale. And that will be a, say, 5 by 2. So current is crossing the same way as voltage is moving. So both voltage and current will have the, let me write down, both Vs and ID will become 0 at omega t equal to 0 and 5. Am I correct or not?
Yes, sir.
Okay, so then current through your diode D1, D2 will be 0 here, and the voltage is going negative. That means it changes its direction from negative to positive here. So look here, in that case, the diode D1 and D2 will be reverse bias, and also it will stop conducting. So what was the condition to stop conducting any power electronic device? I have already mentioned it.
Sir, reverse bias would.
The devices must be reverse biased, as well as the current through it must be 0. Current through those devices must be 0. So we see that D1 and D2 already reverse biased here, and current is also 0 here. So on D1 and D2 will be stop conducting after omega t equal to pi. Let me write that. Since I is equal to ID equal to 0 at omega t equal to pi, and also at omega t equal to pi plus Vs is negative. D1 and D2 must be off. You got my point?
Yes, sir.
Now, in the negative half cycle, look here, since it is positive, then current will move from this way and this way and this way. D3 will be conducting, and the current will have the same direction through your resistance, and it will go this way, this way, this way. Okay, sir. D3, right? D3, D4. Yeah. So it must go. Then it must flow this way, this way, this way, this way. So during the negative half cycle, D3 here, D1 and D2 will be conducting, and from negative half cycle, D3 and D4 will be conducting. And the current, look here in the resistance or in the load, current will have the same direction for the positive half cycle and negative half cycle. I will correct or not. Look here. This is for the negative half cycle direction of the current, and this will be the current direction in the positive half cycle current. So current will have the same direction in the resistance for positive and negative. So for the positive half cycle, we have already got the output wave shape like this. So since the current will have the same direction through the load, and we know that Vt will be nothing by Id multiplied by R, so we get the same wave shape here. Oh, this is the ID, right? What about the IS? What about your IS? When the current was flowing through your D1 and D2, let me insert the okay. This is your D1 and this is your D2. So current has when D1 and D2 was conducting, current was flowing like this, and IS will have the say it is equal ID equal to IS. Actually, IS equal to, I should say, ID. This is IS. So we got this one. But here in the negative half second, we see that the current will change the direction in the source side. It is going opposite what we have already taken. You got it or not? Hello?
Yes, sir.
Yes, sir.
So it will have the negative direction. This is your IS. This is IS. But IT will have the same direction. That is why we get the DC voltage, right? Now, if we want to get the average value of the output voltage, say VD, so we want to find out the average value of the output voltage, okay? How we can take the average value of the output voltage? Can anyone tell me? We can integrate it, find out the area of the, okay, if this is the wave share of the voltage, this is your VDT, and this will be say VDT, and this is the peak value, root to Vs, and we know the equation, right? So we can get the area. How can we get the area? How we find out the area?
Sir, integration করতে হবে.
Okay, then integrate it 0 to pi, and you know the equation will be root to Vs sine of omega t and t of omega t. So that is your area.
So divided by
Then you
the
have-
time side.
Then you have to divide it by pi, and that will be your average. This is capital V. Sometimes people call V0, V average, whatever, VT. And if you solve this one, then what you should get? You should get root to Vs by pi, and this one is nothing but 0.9 Vs. Okay? You understand it or not?
স্যার এটা কি ইনটু 2 দিয়ে মাল্টিপ্লাই হবে? কারণ আমরা তো পাই টু 0 ধরেছি, কিন্তু একটা ফুল সাইকেলের জন্য তো এরকম দুইটা
Let us do that. Let us do that. 1 by pi, then so root to Vs minus cosine of omega t, then pi 0, right? Root to Vs by pi. Then if you substitute pi here, then this is 1, and minus minus, this is minus and minus plus 1. This is 2 root 2 Vs by pi. You got it or not?
ইয়েস স্যার।
Yeah, this is nothing but your same, we got it output voltage 2 Vm by pi. That means 0.636 Vm. We have already done this thing, right? If you replace it by root 2 Vs, that means your, in terms of RMS value, then you should get 0.9 Vs. For the full wave, for the half wave, what it should be? Can anyone tell me? For half wave? Just half, you will not get this part. This will be 0, right or not?
স্যার ভিএম বাই পাই, ইয়েস।
Yeah, that means 0.45. For half wave it should be 0.45, 0.45 Vs or Vm by pi. Is it clear to you?
Yes, sir.
Hello. So the wave shape of this current IS is sinusoidal. Here. Let me talk some of the thing. Suppose this is the wave shape of the IS, which is going like this. And also this is your IS. And I'm plotting on the same graph. Time scale will be the same. So suppose this is your VS. So VS will have the root 2 VS sine of omega t, right? Where omega is equal to twice pi f. Now the frequency f equal to say 50 hertz. What will be the frequency of your current?
স্যার একই হওয়ার কথা না?
Why you are telling হওয়ার কথা? Same.
হ্যাঁ স্যার, যে পিরিয়ডটা তো সেম, টাইম পিরিয়ড সেম।
Yes. So it is same, right? That means it is not distorted at all, and it will have the same frequency. Then we tell that the current for the resistive load, current means input current, right? Not the output. Input current for the resistive load is purely sinusoidal, as the same as the voltage source. You understand it or not?
Yes, sir.
Yes,
So,
sir.
and it is not distortion, so we say IS does not have other frequency component component except fundamental frequency. I'm just introducing all this term fundamental frequency. You must know the term fundamental frequency of 50 hertz, right? We have only the one frequency, that is the fundamental frequency, that is the frequency that has come from the source. So no other harmonics, no other frequency means no other harmonics. Okay, if a current is non-sinusoidal, then you can do the Fourier analysis. The Fourier analysis will be, say, this one. There could be a DC value. Then n equal to 1, 2, 3, infinity. A n cosine of n omega t plus n cosine of n omega t. Do you know it? Fourier series.
Yes, sir.
Yes, sir.
So yeah. Okay, so here your an will be 0 and bn will be yes, bn will have the only the n equal to 1 value and DC value will be 0, so you will have only the, so you will not get any component in equal to 2, 3, 4, 5. You got my point. That means only the single frequency, the first harmonics, the fundamental frequency will be here, and if you do it, that will be your output voltage. You already this one, say this is your IS current. Then what will be the expression of this one? Can anyone tell me? Is by R. Am I correct or not?
Yes, sir.
So root 2 is by R sine of
Negative.
t. Even there is no phase displacement in phase. I hope you have understood what I am trying to tell you. Any question?
No, sir.
Sure?
Yes, sir.
Any other people? Hello, I am waiting.
No, sir.
No, sure. Are you sure?
Yes, sir.
Okay, good. Now let me clear these things out. Now we shall analyze the single phase rectifiers for highly inductive load. Highly inductive load. So what does it mean by highly inductive load? Suppose the load has lot of inductance, but resistance is almost zero. Almost zero. We call it L equal to much high. Okay, let us draw the rectifier again. Here, this is the load, and this load is much higher. Then still we are keeping your input inductor zero, source inductors. D1, D2, that is your D3 and D4. And we see that we have already know that the output voltage ratio will be like this. And the current, look here, the current, it will not, the current will not be, the current, say ID, and this will be say VD, this is VD. The current will not be like this, what we got for the resistive load, rather than current will not be changed, because what is the characteristics of the resistance? Can anyone tell me what is the characteristics of the resistance? What is the characteristic of the, what is the characteristics of the resistance? Tell me. It will oppose the current, right?
Yes, sir.
What is the characteristics of the inductance then?
It will oppose the abrupt change of current.
Rate of change of current, right?
Yes, sir.
So if inductance is very high, then it will not change the current. Like it will not allow to fall the current here. Rather than it will keep.
It will have a high discharge rate.
Yes. So, and I don't know whether the terms are known to you or not. There is a time constant.
Yes,
RL.
sir.
So
Yes, sir.
this RL is very high, so it will not go to zero. So you will get, essentially you will get a constant current. So we can replace this one now as a constant current source rather than resistor. So this ID will be say capital I. So if you get this kind of load in the load side, then you will assume that the inductance is very high. Can you tell me what will be the example of the highly inductive load?
Highly inductive.
Yes, that means
Sir,
current will be almost constant.
air conditioner.
Okay, we have motor load will be there. Suppose you are
Yes, sir.
using a DC motor, and this DC motor has the lot of inductance, so the current will be almost constant. Okay,
Yes, sir.
very large DC motor will have these characteristics. Okay, let us analyze this one now. I am drawing the same figure. Okay, so this is your why I am drawing again and again, so that it will be easier for you to draw. Sometimes you cannot even draw a rectifier circuit. So this is your VS and now this is your IS, and this is the load side, and this is your say ID equal to capital ID, and the output voltage will be here VD. T. Of course, this is T. And what is VS? Can I tell me quickly? What is VS? Root 2 VS sine of
Negative.
omega t. Okay, now let us analyze this one. If I want you to draw the input voltage, you immediately draw it like this, right? This is pi and this is pi. And what is this voltage? What is the peak value?
Sir, root 2 VS.
Now I am plotting the ID. This is your time, omega t. So I want to plot ID. What will be the wave shape of ID? What will be if I want to plot it? What will be the
Sir, is it a current source?
Constant current? I have already plotted few moments ago. Hey,
So it will be a constant current, sir.
it will be a constant, right?
Yes, sir.
So what is this value as per the circuit?
ID.
Capital A. Now, so look here, the current through the load is constant. Now, for the positive half cycle, which diode are supposed to conduct?
Sir, positive half cycle এর জন্য D1 আর D2.
The D1 and D2 will be conducting for the positive half cycle. And if you then D2 and D3, sorry, D3 and D4 will not be conducting. So of course our output voltage will have the wave shape like this. VD will be VS, right?
Yes, sir.
Yes, sir.
So okay, red one and hashed line is your say VD. Okay, then current is not zero, right? It is the current. Okay, now the current is, I am plotting the path of your current. So it must come from the source and D1, then through your load and D2, and it will go back to the source, right? So, and you already know the current in the output side, and this is constant. Then what would be the wave shape of IS? If IS equal to ID, and this is capital ID.
IS will also be constant.
Okay, good. So this portion, this is your pi, and this is your pi. So we get this one, right? This will be IS. Am I correct or not? Hello?
Yes, sir.
Okay, then in the negative half cycle, your D1 and D2 will stop conducting because D3 and D4 are ready to take over, right? And then what will be the here? So now, what is that change in this direction, negative to positive? The current will flow this way, this way. Just hold on. I would like to wait for a minute. Okay, I'm back. So you got it right. From 0 to pi, our current IS and ID will be same and it is constant, so we'll get it. But the negative half cycle, look here, D3 and D4 will be conducting and the current will go this way. In the load, it will be the same, but in the IS side, it is opposite what we took in the first positive half cycle. But the way, but the magnitude will be same. Then what will be the wave shape of the current in the negative half cycle? Hello. Hello.
Sir, can you
Sir,
please repeat the question?
Okay. What I want to say that the current in the load side will be the same direction, but in the source side, it is opposite whatever we have taken in the positive half cycle. So what will be the wave shape of the current IS in the negative half cycle?
sir, minus IS,
Minus ID actually,
ID, sorry,
right? Because look here, the current has changed its direction. So now is it sinusoidal or it is rectangular? IS.
rectangular, sir.
Square wave.
So then look here, we'll have the same output voltage, this one, and we can find out the what is that? The average value, VD average, that will be same as before 2 Vm by pi or root 2 Vs by pi. That means 0.9 Vs. But here you have contaminated, we have contaminated the source current. Our source is positive voltage. Let me repeat, this is very important concept. Source is positive, source is sinusoidal, but the current, source current is non-sinusoidal and it is rectangular. So I'll now discuss about this current. Okay. So now here, and can I take off the circuit? Let me write something. So since it is not sinusoidal, but it is periodic, so can you apply the Fourier series analysis? IST will be here. What will be the DC value of this IS? What is the DC value of this IS?
Sorry, it has no DC offset, sir. So then shouldn't it be 0?
Yes, average value will be 0 because whatever you are getting, say, in the over one cycle, positive.
It will cut each other.
Yes, it will be the same as A and B and also negative, right? This is the negative. So if you take the average, means that you add this area with this area and this is equal and opposite, so you will get the 0. So you will not get any DC value. Am I correct?
Yes, sir.
Then n equal to 1, 3, 5, infinity, n cosine of n omega t plus bn sine of n omega t. You will get only this part, right? And also, look here, n is equal to 2, 4, 6. An will be 0 and bn will be 0. Do you know it? If you will get any wave shape that is symmetrical over x-axis, then even function of n, even harmonics, n equal to 2, 4, 6, 8, 10, you will not get it. Do you know it or not?
Yes, sir.
So you will only get odd harmonics. And also, you will not get anything, n will be also 0. So eventually, what you will get IST will be your Vn sine of, if you put 1 omega t, then Vn sine of 3 omega t etc., etc. And also I should have done. Or let me write on this way, it is better. Root 2 is1 sine of omega t. S1 means this is the RMS value of the input source current, and root 2 means that you are getting this is your IM, that is the maximum value, and then you will get root 2 is3 sine of 3 omega t. Then you will get root 2 is 5 sine of 5 omega t, etc., etc., right? What is omega? What is omega? Hello?
Sir,
2 pi f, sir.
Twice pi. And this F is what? The frequency of the source voltage, right?
supply voltage.
So, yes.
50. We call it fundamental frequency, okay? So we'll get this fundamental frequency as well as we'll get triple of this frequency, and we will also get say 250 hertz of the frequency component like this. And this is we call it the RMS value of the fundamental component. We call it third harmonic component of the RMS value. We call it fifth harmonic component of the RMS value. You got my point on it?
Yes, sir.
Okay. Now we have to find out. Unknown is IS1, right? We don't know what is the IS1. We have to find it out. Okay. Let me try to find it out by using some equation. You can find it out by using Fourier series, but Fourier series is very difficult to do that because you have to do integration and then you have to put n equal to something, n equal to 1, 2, 1, 3, 5, all these things. All these things you have to finally get the peak value, then you have to divide it by root 2, then you will get the RMS value. But there is another easy way to do that. Let me now clear it out. The easiest way to find out the value of the IS1, I am trying to establish here, that is nicely given in your book in chapter 3, the mathematics 6. Okay. So the power, the input power will be, say, input will be 1 by, say, T1, 0 to T1, then instantaneous power T, dt. Then 1 by T1, 0 to T1, and Vs, T, then Ist. You got my point? Yes or no? And then
Yes, sir.
this is 1 by T1. This is given in your third chapter, chapter 3. So this is given already. Vs sine of omega t. Now our current is rectangular, right? But our voltage is sinusoidal. We have to find out the fundamental component of the current. What will be the fundamental component of the current wave shape? Will be like this. This will be the fundamental. Why it is fundamental? Because it will have the same frequency of your input voltage. Am I correct or not? So that is your IS1. So we have to take this IS1 here. So then that will be your root 2 IS1 sine of omega t minus phi 1. What is phi 1? What is phi 1? Phi 1 is the angle between the sinusoidal component of the input voltage and sinusoidal component of the input current. Sinusoidal component of the input current in the same frequency will be the IS1. So this is the phase angle. Here, what is our phase angle? What is our
0.
phase angle? 0, right? You are correct. So if you complete this equation, then you will get IS1 cosine of phi 1. Okay, this is your input power. What will be your output power? This is the rectifier. What is the output, DC or AC?
DC.
P out equal to P DC.
ID into VD.
Yes, VD multiplied by ID. All the DC component, right?
Yes, sir.
So we have already found this average value or DC value 0.5, 0.9 VS, and that is your ID, right? Am I correct or not?
Yes, sir.
Now, if you think about the lossless transmission, that means lossless conversion, I should say, then your P in must be equal to your P out. That will be VS IS1 cosine of phi 1, and then this will be V equal to 0.9 VS ID, right? From here. Yes or not?
Yes, sir.
Yes, sir.
Our phi equal to, as we have already mentioned, there is no phase difference, it will be 0. And your VS cancel. And from that one, I can write down IS1 will be 9, but nothing but the 0.9 of multiplied by IS. Oh, sorry, ID. You understand it? What is ID? What is ID? What is ID? This is the average value. Yes, this is the load current. That is means the constant current that is added to your output side. Okay. So in a nutshell, what should I say is that the RMS value of the first harmonic component, input current, let me write down the RMS value of the first harmonic or fundamental component of input current, input or source current, input or source current will be then how much in terms of output current? How much? Tell me. IS1 will be. Hello, are you with me?
Yes, sir.
0.9 ID. Okay. You are not saying anything, then how can I know you
Sir, how is it 0.9 ID?
Input voltage, input power was IS1 cosine of phi 1. Did I drive it?
Yes, sir.
Output was VD ID.
ID.
VD is equal to 0.9 VS. And this is your ID. Phi 1 equal to 0. Then your VS IS1 will be your 0.9 VS ID. This VS cancel. Then IS1 will be what?
0.9 ID.
That I am trying to tell you. Yes or not?
Yes, sir.
Hello. Okay. Okay. If you have a rectangular wave like this, and if this is say this is your IS, this is your pi, and this is your price pi, and this is your capital ID. What will be the RMS value IS? You have to square it, then you have to take the RMS means RMS. Square it, take the mean, then take the root. Then you will get the ID. You check. So RMS value of the total current will be what? RMS value of the total current will be just the peak value of the current. You understand it or not? You
Yes,
can
sir.
do the mathematics later. And but the first harmonic will be the 0.9 of ID. That means 90% of the
90% of the RMS count.
RMS. Right. Okay. So there is a relation. How you will find out the other harmonics? How will you find out the other harmonics? Okay. So there is a formula S is, this is 0, and then that will be a let's leave them. Okay, yes. That will be 0, and this is IS1 by H. This is 0 for even harmonics, even values of H. That means when H equal to 2, 4, 6, etc. And when H equal to say 1, not 1, 3, 5, 7. You want to find out, say, H equal to 3. Put H equal to 3. Then IS3, the RMS value of the third harmonic component will be IS1 divided by 3. What you have already got, IS1 equal to how much?
0.9 ID.
0.9 by 3. You understand it or not?
Yes, sir.
Okay, now if you want to plot,
Sir, so for the harmonics, we can get the magnitude.
yes. Okay. Suppose you are now with respect to H, you are trying to plot ISH by say IS1. So what will be the first harmonic there? IS1, put H equal to 1.
Yes, sir.
So that is 1, right?
Yes,
It
sir.
will- Then third harmonics, 3, 5, fifth harmonic, 7. You just put H is equal to 3. So you put H
Sir,
is equal to,
isn't
it
it
will
like gradually they will
yeah,
continue
this
to
will be
become
1, 3.
insignificant?
Yes, 1 by 5. This will be 1 by 7. So higher harmonics component will have the very insignificant
Contributions.
contribution to your current. Actually, the most, like this is, look here, this is almost very much close to sinusoidal. That is why, and also it is 1/3 of the fundamental value. You understand it or not?
Yes, sir.
Okay. The other thing I want to now mention here. So after all, what I am trying to tell you is that we have contaminated the input current, right?
Yes, sir.
And it is no longer sinusoidal, rather than it is
Square wave.
square or
No,
triangular,
sorry,
right?
rectangular.
Oh, sorry,
Yes.
rectangular, not triangular, rectangular. Because we don't know, to say square, your half cycle width must be equal to your height, right? That means,
Yes, sir.
oh, okay, now, so how much you have distorted your input that we want to find. So there is a factor, they call it total harmonic distortion. Total, it is very famous factor, total harmonic distortion. Usually that is expressed in the percentage. So total harmonic distortion will be your, the formula is 100 multiplied by IS square minus IS1 square divided by IS1. So do you know IS? in terms of ID. I is equal to ID. So do you know IS1 in terms of ID?
0.9 ID.
And this is your 0.9. And if you do that, you will get 48.43%. So that means, so this is the total value of your harmonics of this input current, and you have squared it, and this is the fundamental value of your input current sinusoidal. Take the RMS value, square it and negate it, and take the root over and divide it by the fundamental component, and you will get the result, and it is 48.43%. That means we have distorted our value. This part is also known as the distorted part. This part is also known as the I distortion. Okay, so how much you have distorted? You have distorted the signal input source, input current by 48.43 from its sinusoidal, and that is not acceptable at all, because the utility, you are taking the sinusoidal voltage, but by just putting your load in such a way, inductive load or very high, say high, very large value of the DC motor, you are connecting to the rectifier, and you are getting the input current rectangular type, and you have distorted. So IEEE, they have suggest you cannot make this total harmonic distortion more than 6%. It will be within 6%. You understand what I want to say? How can
Sir.
you do that? Yes.
Yes, sir. I was also actually asking this, sir. How can we actually do this?
Yes, that is the a lot of researches are going on. People are using filtering, people are using some switching in the input side and some output side. New idea they are proposing to reduce this total harmonic distortion. And also we shall find another factor that is known as input power factor. You got my point? Input power factor. So current is now non-sinusoidal. So power factor will not be, input power factor will not be 1. So how can we find out? P equal to, we have defined it, cosine of phi 1. Do you know S, apparent power?
Yes, sir. BSIS.
BSIS. So input power factor will be your multiplied by S, that is your input power, must be equal to your VS IS1 non-sinusoidal cosine of phi 1. So input power factor then come as VS IS1 cosine of phi 1. For our case here, we see that phi 1 equal to 0 and S equal to VS IS. This cancel. So we are getting IS 1 by IS. This 0.9 ID divided by ID. It is coming as 0.9. So input power factor is not also 1. We want input power factor 1. So there is another factor we call displacement power factor. Displacement power factor. So this is defined as cosine of phi 1. That means this one. This one is the displacement power factor. So for our case, how much it is? What is the phase difference between your current and the voltage? Phi 1 is what? 0. So displacement power factor will be 1 for this case. You understand it or not?
Yes, sir.
Yes, sir.
Okay, so inshallah, we shall start class for analyzing more when there will be LS. That means if there is any source inductance, what will be the effect? That we shall inshallah analyze after your midterm. Okay, so this class will not be included in the midterm. You understand it?
Yes, sir.
Before the class, we will have that. So the other students, they are keeping 100% silent. What happened to them? Are you with me? How many students attended this class?
Sir, actually,
41.
we had classes from early morning, sir. This is why many of us are actually exhausted by now.
So why did you take
Continuous
that?
class.
So okay, so then you can shift after the midterm. You can shift this one. Okay.
Okay, sir.
Yes.
Sir,
If you
I have a question from the previous slide, sir, if you would go.
Okay, you say, you tell me.
Sir, you have said that the phi 1, I mean, there is no difference, it is 0. But sir, we are actually using a highly inductive load, sir, right, sir? So shouldn't it be something like close to 90° for the inductive effect?
So you're talking about the out. Okay,
Yes, sir.
I am coming back. Your question. First of all, you were talking about like, first of all, you were thinking this way. This is your inductance like this, right?
Yes, sir.
But that is not true. Rather than our input will be like this, because that has been connected. So you have the rectifier here. This is sinusoidal, but from here you will get this one that has been connected to your inductance. You understand it or not?
Yes, sir.
So it is not so. So there is no way to think like this. The current will lagging this one by 92 because this is the input current. This current will go, of course, here. And we have already seen that the wave shape of the input current will be like this. It is not your sinusoidal. Your current will be, your voltage, input voltage will be this one, but the input current will have the wave shape of this one. So that is your IS. So what is the phase difference now? Tell me, between your input current and output, sorry, input voltage and output, input current from here.
Sir, 0.
0. Here, I told that your inductance will be very high. So your input voltage is like this. But since highly inductive load is there, or high inductance you have inserted, so the current, the discharge will not be there, rather than the current will be just DC. You got my point or not? This
Yes,
is your
sir.
this is your output voltage, but your current will be constant because you have inserted very, very high inductance. You understand it?
Yes, sir.
And current is not sinusoidal, rather than it is rectangular. Rectangular, right? Now, if you do the Fourier analysis, you will see that current wave shape will be, the current wave shape will be like this. And this is the fundamental component. And what is the phase difference between this fundamental component and VS? What is the phase difference? Tell me. Look here. Here.
Sir, can you repeat again?
What is the phase difference between between VS and IS1? Look at the figure.
So 0, sir.
0.
And this is not this phase difference is known as phi 1 and this is 0. And cosine of phi 1 will be known as displacement power factor. And since it is 0, so for this case, we are getting 1. But input power factor, we have already found out. What is the input power factor? It cannot be seen by the wave shape because this is your rectangular type current, and we have already found this is your 0.9. What we want, it must be as close as 1. Is it clear to you or not?
Yes, sir. It is clear now, sir.
Okay. So, okay, let me, only 41 students are here. So I must take the attendance.
Sir, I'm stopping the recording, sir.
Yes, please.